Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 5.1.2, which is multiple representations of quadratic functions. In today's lesson, we're going to be looking at how a quadratic function can be represented. And when they talk about multiple representations, what they really mean is, in the context of this problem, we're dealing with a water balloon contest where balloons are being shot into the air and coming back down. So hopefully you can imagine that happening, where if a balloon is launched from, say, the ground, it'll launch and hit an apex point and then come back down and land back on the ground, forming an upside-down parabola. So we should be seeing a lot of negative parabola equations in the data that we extrapolate, which should make sense compared to last when talking about last lesson, where we saw that when there was a negative in front of the parabola, the U shape was upside down. So hopefully that should chime well with what's going on. There's a lot of exposition in the problem. I'll have you go and just pause and read the question about Newton High School and the water balloon contest. There's a lot of exposition here about the people. But basically what you need to get out of this when all is said and done is that the first contestant, this person called Magnanimous, when she runs down and shoots her balloon from the 3-yard line, after the launch, the computer reports that the balloon traveled along the parabola represented by this function. So this is Maggie's parabola right here. So we have to keep that in mind. Then the next person is Generous, who she runs down the field, and unfortunately the computer reports it as a graph and not an equation. And then comes this dude Impeccable. When he launches, the computer only represents it as a table. And then this last person, Altruistic, the computer is completely fried at this point, and all we know is that he launches from the 10-yard line and it reaches a maximum height of 27 yards. And it does land at the 16-yard line. So again, multiple representations of the quadratic function. We're just going to use all 4 of these representations to somehow extrapolate data about each of their water balloon launches. So again, what are the representations? An equation, a table, a graph, and just some information that may or may not be helpful. So when we get back into part A, after I pause and grab it from the previous screen, we will find out some of the information about each of their launches. So I'll be back in a flash. And here we are. It says, finally, the announcer calls for the last contestant Altruistic. Oh, we already read that part. Sorry. So part A says we have to obtain a resource page, which I have copied and pasted, and then we have to basically analyze the data for each of the contestants. And so we have to determine which of these contestants should win for the longest distance and the highest launch. So let's go ahead and compile the data real quick here. So right now, the first graph up here, this is Mags, and what we're going to do is we're going to compile her distance, and her distance, hopefully it makes sense because we talked about this in the last section, the distance from launch to landing, hopefully it makes sense that those would be the X-intercepts of that graph. So the distance from here to here would be Mags's total distance horizontally. So it looks like the balloon landed at 14, even though it was launched from 3. And whoa, that wasn't supposed to happen. There we go. And even though it was launched from 3. So it looks like her horizontal distance, I'll just call it H distance, looks like was 14 minus 3, which is 11. So Mags's total horizontal distance was 11. Now, the weird thing about Mags's data here is that if you put it into the table, which you should have, you're going to split down the middle here, which doesn't actually, cross a vertex at a really clear place. And so honestly, I really wish I would have done this last, because that way we know how to deal with such an eventuality. But if you look at the table, it looks like these two places are equal. And so since that's in between 8 and 9, I can only conclude that at a horizontal distance of 8.5 is where Mags ends up getting this distance from. Now, the way we're going to calculate the actual apex of that water balloon is we're going to plug 8.5 into the function. So if I do y equals negative 8.5 squared plus 17 times 8.5 minus 42. After a bunch of calculations, you should get 30.25. Now I'll go ahead and just verify that in Desmos here. And I'll go ahead and go to the apex here, 30.25, 8.5 comma 30.25. I think I'm solid. So from here, that means that Mag's vertical distance is going to be 30.25. So these are her two distances here. Horizontal distance of 11, vertical distance of 30.25. Let's go and compare that to Impeccable. So Impeccable, in his table, he starts off at a launch at the 2-yard line. And then if we look at the data here, look at how the symmetry begins at 7, 25. So that lets me believe that Impeccable, his vertical distance is going to be easiest to find first. So his vertical distance is going to be 25 feet in the air. And so now from here, notice how the values here are matching, the 24 and the 24 and the 21 and the 21. This symmetry is really important for a parabola because it helps us find the next points very, very easily. Without even plugging in, I'm hoping you can determine what the point 10 is going to give me because it's going to link up with this 16 right here. The 10 is going to get me 16, and 11 is going to get me a 9, and a 12 is going to get me a 0. Again, I just based that off of the symmetry, right? So 9 will link up with this 9 here. We already saw the 16s link up. And then 0 should match up with 0. So from here, that should make Imp's horizontal distance easy to calculate. The distance between 12 to 2, that distance is 10. So comparing those two, it looks like Mags has already beaten out Imp pretty clearly in both arenas. So let's take a look at Jen's data. Jen launches from 0 and ends at 8. Again, what's this distance right here? This distance here is a distance of 8. So Jen's horizontal distance is 8. And her vertical distance, though, is way up here. So if I look at how this thing's being scaled, if I go, let's see, 0, 1, 2, 3, 4, 5, looks like the y-axis is in fact being scaled up by 1. That means that her vertical distance is up 32. So her vertical distance is up 32. So it looks like Mags is still in the lead for the horizontal distance, but Jen looks like she beat out Mags for the vertical distance here. Let's come back and talk about our good old buddy Altruistic. And our good old buddy Al, he launches the balloon from the 10-yard line and it lands at the 16-yard line. Let me graph that first before we move on because I'm going to take this one step at a time. I'll do Al in yellow here. Here comes Al. And he launches it from the 10. From the 10, it lands at the 16. And I think I just realized that all of this is in yards, not in feet. My apologies. So from here, we know that it reaches a height of 27 yards. So here's the thing, is that what you're supposed to get out of Al's graph is that notice the distance here. The distance between launch and land is 6, which means that at a distance of 13 is going to be his height of 27. So 13, 27, and it's going to come up, hit apex, and then come down. So it looks like Al's horizontal distance is going to be 6, and his vertical distance is going to be 27. So who won? So when it comes to the horizontal distances, I'll go and do this in orange. When it comes to the horizontal distance winner, I believe that is none other than our good old buddy Mags with a horizontal distance of 11. So Mags won that one. And then the vertical distance winner is none other than our good old buddy Jen with a distance of 32. So I'll go and write down their distances here, 11 and 32. Okay, so that is part A. I'll come back for part B in just a second. let's see. In part B, it tells us where are the x-intercepts of each parabola? What information do the x-intercepts tell you about each balloon launch? Well, the information that's given to us about each of the balloon launches is that the x-intercepts are where they are on the ground, right? So mags launched from the 3-yard line, and the balloon lands on the 14-yard line. We can tell that the balloon is launched and lands because the balloon is launched from ground level. So when we look at the xy coordinate plane, right, where y is vertical distance and x is horizontal distance, when the balloon's on the ground, its elevation is literally 0, and that's at the time of launch. When the balloon is on the ground because it landed, its elevation is also 0. So again, those x-intercepts tell you when the balloon is on the ground. In fact, I'm going to write that down. That'll be the first thing I answer. So in B, the x-intercepts tell us when the balloon is on the ground because a y coordinate of 0 indicates 0 elevation. Okay, so let's go ahead and find each of the individuals x-intercepts. I'll go and switch colors here to white here. That way we get something that stands out. Okay, so we got Jen. I'll do Jen first. Look at Jen. Her x-intercepts are 0, 0, and 8, 0. That part's pretty obvious. 0, 0, and 8, 0. Cool. Let's take a look at Mags. Mags is 3, 0, and 14, 0. Again, if we just look back up at the table that we have up here, 14, 0, 3, 0, and we can also see that from the graph. Our good old buddy Imp looks like 2, 0, and 12, 0. So Imp is 2, 0, and 12, 0. And our good old buddy Al, his was 10, 0, and 16, 0. Again, we actually had to graph Al's trajectory because his computer fried up. Okay. Let's take a look at part C. Part C says, where is the vertex of each parabola, and what does this information tell you about the balloon launch? Well, let's take a look at what it tells us first. Well, the vertex is where the balloon is going to apex. It's the highest point of the parabola. And so let's go and write that down. Get it down over here. So in part C, the vertex tells us the highest point of the water balloon launch. In other words, the highest elevation the balloon reaches. So let's go ahead and take a look at each of their vertices. And so again, we'll go back to Jen. We saw this earlier. Hers was at 4, 32. How can I tell? Well, remember, in each of the examples, even in the last lesson, we noticed that the vertex of the parabola was always in the dead center of the x-intercepts. So at 4, 32, there goes Jen. Mags, we actually had to calculate that one, and we saw that earlier in this episode, where it was 8.5, 30.25. Imp, if you look at his table, his is going to be at 7, 25. And again, we talked about that because that point of symmetry where things started to repeat, it was at 7, 25. And then, of course, we found Al's manually because we determined that his horizontal distance was 6, which meant the individual distances from the x-intercept to the vertex would be 3 each, so 13, 27. So here comes Al. 13, 27. Okay, so that takes care of 5-16. That's only one part of this lesson. I'll be back with the next part in continuing our journey of multiple representations of our quadratic functions. I'll be right back. In 5-17, we're introduced to a new character, Sasha, who is now tracking the results of the water balloon contest, and she pays special attention to Mags's balloon. And she wants to determine how high up the balloon is when it's directly over the 2-yard line. And so she knows the equation for Mags's balloon is this. And so let's take a look at this. If I plug in f of 2, that's going to look like negative 2 squared plus 17 times 2 minus 42. Well, that's going to give me negative 4 plus 34 minus 42. And that's going to simplify out to become 30 minus 42, which is negative 12. Now, here's the thing, is that what they're saying is that at this point in time, at the 2-yard line, Mags's balloon is 12 yards below the surface of the Earth. And we're trying to figure out, does this actually make any sense? What does this answer tell you? Well, this answer tells us that Mags's balloon is below the Earth. That can't happen, right? And so what this problem is trying to get at is it's trying to say, look, this parabola, although parabolas do have a domain of all real numbers, right? Because in the last episode, we saw that these arrows allow the parabola to keep on going. Because this parabola is simulating a real-life scenario, we now need to restrict the domain of this parabola and restrict the range of this parabola so that it can actually model what we need it to model. So in part B, it says to write an appropriate domain and range for the model of the flight of Mags's water balloon. We got to explain. So I think an appropriate domain for Mags's water balloon would be to begin at 3 and to end at 14 and have x in between them. Now, x can actually be those values because it actually does, in fact, get there. An appropriate, then, that'll be my domain here, domain. And then an appropriate range would be from 0, right, because the balloon is at lowest on the ground, and it reaches a highest point of 30.25, and that's going to be my range for y. Now, again, why is this appropriate? It's appropriate because the balloon's never going to go underground unless someone actually did dig a hole, in which case the problem would have indicated that. Ordinarily, a parabola's range, if I was to graph this thing outright, what we would have is we would actually have those arrows going down. And they would go down forever and ever and ever, which means y would have to be all values less than 30.25. But again, we're talking about the balloon never going underneath the Earth, which is why the domain can't extend beyond 14, because clearly the graph goes to the right of 14, but at this point the balloon is underground. So hopefully that makes enough sense for why the domain and range is what it is, because we are trying to simulate a real scenario where the balloon really wouldn't travel beyond 14, because by the time it landed on the floor, it would presumably explode and no longer exist. So hopefully that makes sense for part 17. I'll be back with part 18. And in the last problem here, we are doing from a tile pattern situation to an equation. So again, we're reinforcing this idea of how to represent a quadratic equation in multiple ways. If we look at all these tile patterns here, it seems like they're growing by quite a bit. And so, but the one thing that seems to be consistent among all of them is that there's always like these 2 blocks hanging on the outside. These 2 blocks. So it looks like in every situation, looks like I'm going to be adding 2 each time to each situation. So hopefully we can get that locked in. And now when it comes to how these things are growing, if you look at figure 1, figure 1 has 1 block here, right? And it seems like we add another block to it. So this looks like it's 1 block and then plus 1. The same block here, or the same length, could be seen as a 1, right? Again, figure 1. But this time, it looks like you're adding 2 more to it. Okay. In figure 2, it looks like there are 2 blocks, right, along the side. And it looks like you're adding 1 to it. So again, I'll just say 2 plus 1. Those same 2 lengths right here is going to be here. But it looks like you're adding 2 to them as well. And then figure 3, as you guys can probably see by now, looks like there's 3 of these side lengths plus another 1. So I'm looking at 3 plus 1. Those same 3 heights will be 3 and then plus 2. So if I had to describe in words how this tile pattern is growing, I'll go and just do it here, down here. If I had to describe in words, I would say the tile pattern is growing with a figure number plus 1, and that seems to be like the length of the shape. And then there's figure 1 again, figure 1. or figure number in this case. And it looks like I'm adding 2, and that's the height. And there always seems to be this plus 2 hanging on the outside. So if I had to figure out the area of this, I'm going to write an equation to represent figure x. So that would be figure x would just be, instead of 1 plus 1, 2 plus 1, 3 plus 1, it would be x plus 1 for the length. And then instead of 1 plus 2, 2 plus 2, 3 plus 2, it would be x plus 2 for the height. And then this plus 2 would hang out on the outside. So that would be an equation that I would have to represent the number of tiles. And then, is the equation from part B quadratic? I'm pretty sure it is. Because if I multiply this thing out, right, if I'm going to rewrite him, x plus 1 times x plus 2, if I multiply them out, I get x squared, there's my leading term, plus 2x plus 1x plus 2. I get x squared, oh, don't forget about that plus 2 right there, x squared plus 3x plus 4. Ends up becoming a function if I wanted to write him as such. So there you have it, a bunch of different representations for quadratic equations. Hopefully you found this useful. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.